तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody, welcome again to the lecture on computer graphics. In the last lecture we started to discuss the concepts of scan line method based line drawing, okay, and we are discussed first the difficulties of drawing a line given the specifications of the starting point and end point of a line, and whereas in the continuous case we could draw a line, but in the discretized domain we have to fit a set of addressable pixels with respect to the integer x and y coordinates, and to do this we had to find out the set of pixels, the integer coordinates of pixels which were closest to the line, and we had to do this very fast, as possible, so that the computational time or the cost is the minimum. We looked at first an incremental algorithm called the DDA algorithm, digital differential analyzer or digital difference analyzer, and we had seen that it was a costly algorithm because the steps involved were using a round function and a floating point addition. So to eliminate the round function and to and also to eliminate the floating point operations and move towards integer arithmetic, integer based addition, which will provide a fast method to produce the xy coordinates of the points which are closest to the line, we moved on to the concept given by Bressenham's, which is called the Bressenham's algorithm or midpoint line algorithm, and we have discussed the condition of midpoint criteria to find out whether the midpoint of the second or the next point is below or above a line. So, we will start from the midpoint criteria, revisit it again to maintain the continuity, and then look at the steps of the algorithm and look at an example as well as to how the points could be generated to draw a line on the screen. So, if you look back, the midpoint line algorithm is an incremental algorithm, and we are working assuming the first octant, and we will also see today how the other 7 octants in the 2D space are handled, and the assumption on the first octant for drawing a line puts a constraint that the slope of the line of the equation y equal to mx plus b, as given here, m is equal to dy by dx, and dx is more than dy in the first octant. That puts a constraint that the slope is less than 1 or the m of the equation is less than 1, and if it is so, then of course that given a current pixel at any stage of iteration, the choice of the next pixel, which could be current or the current after next after current, is between any two options, east or northeast. We have seen a figure also in the previous class, and we are going to see that. We will revisit the equations again, where the equation y equals mx plus b or dy by dx multiplied by x plus b is the original equation of the line, and we try to rewrite the equation in the form fxy is equal to 0, where if we try to write where the coefficients, small characters a, b, c, as you see, are the coefficients or parameters now of the line, and we try to rewrite equation number 1 in terms of equation number 2, we can basically rewrite it equation number 1 in this form, where the coefficient a is equal to dy, coefficient b is equal to minus dx, and the coefficient c is capital B multiplied by dx. So, these are the coefficients of parameters of the line, and that means the equation number 1 takes the equation fxy equals as given here equals 0, and we know that what are the coefficients a, b, c now. as given at the bottom of your screen. And what is the advantage with the help of this equation in a form as given here, the parametric form f x y equal to 0 is that if you select a point which is lying on the line, the value of f will be equal to 0. Okay, because the value of f or the functional form has been derived from the two endpoints of the line, you must remember that, and hence if you select a point which is lying exactly on the line, which can be done in fact almost only in an analog space with floating point numbers, but if able to select that integer or floating point, if the point lies exactly on the line, the value of the function f is equal to 0. Okay. Now, if the point is above the line or below the line, you do have non-zero values of f, one of them will be positive, the other will be negative. This is the basic principle of the midpoint criteria, and we will see when the value of f becomes positive and when will it become negative, depending on the position of a point, whether it is above or below the line. So, the function f splits the line into two parts, a positive half and a negative part below and above the line, and the criteria which we use to evaluate that given this black pixel on the left hand side at the center of the screen is the current pixel which has been obtained at any stage of iteration of obtaining points for the line from left to right in the first octant. The next two choices which remain would be only the northeast pixel as marked in red circle and the east pixel as marked by the blue circle. Okay. So, it is only the next choice can be only between any of these two pixels, and to find out which is the correct pixel of the next choice for the next choice, what we do is basically evaluate the point m with respect to the line. M is a midpoint between east and northeast. So, it is midway between the vertical line between east and northeast, and if you know the current pixel coordinates as marked by the black pixel here, we know the coordinates of the northeast pixel, we know the coordinates of the east pixel as well, because they are just integer coordinates shifted in x and y directions by unity, and we should be able to get the the coordinates of m, which could be a floating point number, but we do not worry about that for the time being. So, the choice as given here will be between east or northeast, and we have to find out what is this choice. So, what we do is take the value of m and substitute in the equation f x y equal to 0. Okay. So, f x y equal to 0 is given by this expression, and we have to assume here that dy, dx and b, these are the three parameters a, b and c for the functional form f x y equal to 0 is known to us. And after it is known, we substitute the value of the coordinates of m in x and y as in this equation, and find out whether f is positive or negative. Okay. So, if f x y is greater than 0, we have seen this condition in the last class, that if it is positive, then the point must be below the line, because what will typically happen is this coefficient will reduce, forcing the value of f to go above 0. And if the point m is above the line or the line passes through below m, that means between m and east, then of course f x y will be negative. Okay, it will be negative because the value of m will have a y coordinate which is more than the value which would have been exactly on the line. So, this term will now force the entire value of f to be negative. So, just remember this, that the function f is positive if the point is below the line as shown here, and f x y is negative if the point m is above the line. So, something which is above the line is a negative world, and something which is below the line is a positive world. If you remember that is sufficient, we are now evaluating a midpoint to find out whether it is above or below the line. The world above actually is negative the above the world below, because the entire 2D space you can assume is split by this line into two halves, and the world above it is actually a negative world on top and a positive world below. Positive below, negative on the top, that is how. So, m is lying on the top, which is above the line m, we will have negative values. If it is below the line, it is positive. So, positive below, negative above is what is, remember, that is the criteria which is used for evaluating the line, or evaluating the midpoint, basically is the correct way of saying evaluating midpoint m with respect to the line, and that helps you to choose to find out easily whether the northeast pixel is closer to the line or the pixel east is closer to the line. Okay. So, this is a diagram which shows that the line passes through in between of course east and northeast pixel, and at the current stage of iteration you have chosen in the previous iteration, let us say the point xp comma yp is the pixel which has already been chosen on the left of your screen, and the line is passing through, it is intersecting the line between east and northeast at a point q, and this point q is above the midpoint of the line. What are the expression of the coordinates of the point E? If xpyp is the previous stage of pixel, then we are trying to find out the current one, or if xpyp is the current and the next pixel must be one out of east or northeast. We know that there are two choices which exist. So, if xpyp is the previous pixel obtained at the previous stage of iteration, then at the current stage what we have is the east pixel will have coordinates xp plus 1 comma yp, and the northeast pixel will have coordinates xp plus 1 yp plus 1. So, what should be the coordinates of the midpoint m? It will be xp plus 1 and yp plus half. That will be the coordinates of the midpoint, because it is exactly symmetrically located with respect to northeast and east pixels. So, difference only will be in the y coordinates, not in the x coordinates anymore, and but the line L, which is the line of interest to be drawn, it is now intersecting the vertical axis between northeast and east at the point q. And we assume now, as shown in this figure, that if q is above m, the world above as we have seen is positive, and so what we see is we substitute the m, the m is below the line. So, we will have a positive value and we select northeast pixel as your next choice. The reverse will happen if the point q is below m. Remember, in the previous figure we had in the previous slide q was above m, now q is below m, or the midpoint is above the line, and if q is either below m or the midpoint is above the line, we can select we have to select east pixel as our next choice, because what will happen is basically that the value of f will become negative now, and the q is closer to m than in the northeast pixel. In the previous figure the q was closest to the northeast pixel, so obviously northeast you have to choose. In this case the q is closer to E than northeast, so you choose east. But how it is closer and which one is closer to q, northeast or east, is basically decided by the value of f after substituting the value of m, the coordinates of m in the functional form of the line fxy equal to 0. So, we can write the midpoint criteria in the form of an algorithm now, and the algorithm for next choice, this is not the full algorithm for midpoint, just the criteria for choice, which is in fact the kernel or the key part of the algorithm or the code which you have to write is the algorithm for the next choice of the pixel is if f of m, that is the functional form or value for the line evaluated at the midpoint, is greater than 0, that means q is above m. That is the figure which we have shown in the previous slide, not this particular figure, but we assume that this case when the value of the functional value fxy equal to 0 substituted by the midpoint coordinates m is positive or greater than 0, then we know that the q is above m or m is below the line, okay, and I'm sorry, m is in fact q is above m in the previous figure, and that is the figure which is given here. I will show the figure here. Q is above m or m is below q. Okay, whatever way you look at it, q is above m and closer to the northeast pixel, or m is below q, and it is under this condition where you will have f of m is greater than 0, and then you select northeast if it is positive, and if it is negative else you select east, that is this particular figure where q is below m or m is above the line q. So, this is the midpoint criteria written in terms of an algorithm, which is the key to choose your next choice. And once you are through with the next choice, you apply the same for the next iteration. After you have selected either east or northeast, that becomes one of these to become your current pixel of iteration, and then you move to the next iteration where the value of xp to xp plus 1 and xp plus 2 is your x coordinate, and you then find out with respect to the choice what is going to be your next to next east or northeast pixel. So, this is the midpoint criteria, the basic principle behind which the Bressenheim-Stein algorithm or midpoint line algorithm works. And now we will go through a few sort of equations to find out where is the integer arithmetic coming in and which speeds up our method to obtain the sequence of points. We move to the next slide, where our basic criteria is evaluate the midpoint m using a decision variable, because that is what you evaluate. You need to find out what m is below or above the line using a criteria, and based on that whether the function value f is positive or negative, you choose east or northeast. So, just remember this principle, and we define a decision variable, that is key to the algorithm. You define a decision variable d which is equal to fxy, and the decision variable d when evaluated at the next midpoint m, that means assuming that at correct stage of iteration or the previous stage of iteration xp yp is the current coordinates, the next midpoint will have coordinates as given here within the bracket of f, xp plus 1, that means x shifted by 1, and yp plus half. That is the integer, that is, I'm sorry, it's not integer, that those are the coordinates for the value m, and you substitute the value of m in this, and I hope you have written and remembering the expression of f which has been written earlier. So, substitute that, and this is the expression which you have. This is the expression which you have for the decision variable d evaluated at point m. And let us say you set this d old at equal to d. This is the old variable. I define a new old variable d old equal to d, and then based on the sign of d, you actually don't have to look into the value of d anymore. You will have to find out whether the decision variable d is positive or negative at m, and based on that you choose one of the east or northeast pixels. So, assuming you have chosen one out of the east or northeast pixels based on the sign of d, you will have two different conditions or two different cases. We will look at the case 1 where you have chosen east as your next choice of pixel. That means when you are choosing E, you must remember that the line is passing below the midpoint m, or the m is above the line. Basically the decision variable is negative. If you remember those two criteria, the sign, the world above is negative, below is positive. So, the line is passing below the midpoint m, and it is closer to the east pixel, and that is the reason why you have chosen E. We will look into the other case where you have chosen northeast. So, look at this first case. Let us look at these equations. Once you have chosen east, the d new, that means the d new is the decision variable evaluated at the next to next midpoint. After the current midpoint is over, we are looking into the next decision variable d new, where the midpoint will now have coordinates. It was xp plus 1, yp plus half. So, what will happen is after you have chosen east, remember the grid situation, the figure given to you earlier, it will come back again. It will be xp plus 2, yp plus half. Why? Because xp plus 1, so you will get xp plus 2, and the y coordinates of the previous midpoint remain the same. So, it will be yp plus half. So break open the expression and rewrite it, we will get this, and the expression given as a xp plus 2 plus b yp plus half plus a. So, that is the new expression d new, that is the value of d evaluated at the next to next midpoint after you have chosen east, and we will say the difference delta d under the subscript e indicates that it is under the case 1 where you have chosen east. That is the difference in the d will be d new minus d old, where d new is given by the expression as given here, and d old is given at the expression, because you have set the d to d old earlier. So, it is given here on the top right of the screen. This is the expression of d old, and this is expression here which is d new. So, subtract this from that, you will get a. That is all, because the rest of the terms cancel out. C cancels with C, b yp plus half cancels with b yp plus half. Here you will be left with only a, because a times xp also gets cancelled. So, the subtraction of d new minus d old gives you a simple term a, and you remember a is equal to dy as given to you earlier, and that is an integer quantity. So, the first order difference delta de, because that is a differential term between the new value of d and the old value of d, is given by a. So, delta d e subscript chosen first case chosen e is equal to a. So, let us evaluate the d under the second case where you have chosen northeast. When do you choose northeast? Line is above the midpoint, or the midpoint is below the line, and when the midpoint is below the line, the functional value is positive. So, the functional value is positive or decision value is positive, and that will probably it will definitely give you the condition that the sign of d is positive and the line is closer to northeast. So, you have chosen the northeast pixel, and if you have chosen the northeast pixel, let us see what happens to the same set of equations. So, we look at case 2 where we have chosen northeast, and that is the figure is given here. So, the midpoint M is below the line, or the point Q is above the midpoint, which is closer to northeast. And remember the expression of d old as given in the previous slide. The new midpoint for d new will be, if this is xp plus 1, the next midpoint will be at xp plus 2 and yp plus 1 plus half, which will be give you yp plus 3 by 2. That will be the midpoint. If this is xp yp, this is xp plus 1 yp plus half for the first midpoint, the next stage iteration midpoint will be moving x by 1 coordinate and also y by 1 coordinate. So, it will be xp plus 2, 1 plus 1, and 1 plus half will give you 3 by 2 or 1.5. So, that is the new midpoint under the second case where you have chosen northeast. You substitute these two x and y values onto the value of f, and this is the expression which you get for the d new. It is a multiplied by xp plus 2 plus b multiplied by yp plus 1.5 plus c. So, this is the new expression of d new, and I hope you have written the expression of d old. So, we subtract d new and d old from d new, subtract these two expressions and get the expression of the delta d under northeast, under the case that you have chosen northeast, and that expression difference will give you a plus b. And you know what are the parameters a and b? They are nothing but, in comments I have written, it is nothing but dy and dx. So, as you see from the previous slide here, delta de under case 1 where you have chosen east, the delta de is a, and under case 2 where you have chosen northeast, the delta d northeast is dy minus dx or a plus b, and both dy and dx are nothing but what? They are the difference in the dy and dx are the difference in the x and y coordinates of the starting point and finishing point of the line. And since the starting point and finishing point of the line, the coordinates are integers, the differences also will be in integer coordinates, and hence these differential delta d terms of the decision variable, which is in fact the update required to update the decision variable d, are also will be integer coordinates. So, if you need to update something incrementally, and if that increment arithmetic can be made using integer values, I did mention you earlier that the algorithm will be very fast. The program will run at a very top speed, and that is the equations tell you that the incremental variable of d, if we will see how that is used now within the algorithm, and that is based on integer values, and it will help you to really speed up the algorithm. But just remember now that based on the sign of the decision variable d, you choose east and northeast, and based on whether you have chosen east in case 1 or northeast in case 2, the delta de will be equal to dy, or delta d northeast will be dy minus dx. You remember these two expressions, and you remember the midpoint criteria for choosing the east or northeast pixels based on the sign of d is sufficient for you to write a algorithm or code yourself for drawing the lines. And if you remember these two, you will be following the algorithm which I will show you next. Remember two things: midpoint criteria, that is based on the sign of d, you choose whether you are northeast or east pixel, and once you have chosen east or northeast pixel, the differential term which you have to add to the decision variable d also will be two values. In one case it will be dy, another it will be dy minus dx as given in the two expressions we have seen in the previous two slides. So, just remember the midpoint criteria and the expressions for the delta d increment, and that these two different conditions of choice, east or northeast, is sufficient for you to follow the algorithm which we will cover next. So, in each case, the last line we say is that we need to update the decision variable d, then to derive the new value of the function d new from d old using the incremental value of delta d. Delta d will have two different expressions, one for the choice east, another for the choice northeast, which we have seen. So, that is what we have seen. Okay. So, the midpoint criteria, we just revisit in the form of an algorithm now. The decision variable d is of course, I will give you an algorithmic form later on, but we visit the entire criteria and the choice and the delta d now. D is f of m, which is given by this expression evaluated at the midpoint, xp plus 1 yp plus half. If d is positive, choose northeast, else if d is less than or equal to 0, choose east. Remember, we are talking of a positive and negative, and we have to worry what happens if in a situation which is may occur very rarely. In a very rare situation, you will have an integer pixel exactly lying on the line. But if it exactly lies on the line, you have to take a decision. In fact, the decision says if the midpoint is lying on the line, your next choice of northeast or east pixel are equidistant from the line. M is now exactly on the line, it is exactly midway between east and northeast. If these are the northeast and east pixels, let us say, and the midpoint passes exactly, and the line passes exactly to the midpoint of the line, and this intersection point Q is exactly midway between northeast and east, then you can choose any one of them. You can choose any one of them is what the algorithm says, but in terms of implementation, one must say here that you must be choosing this east or northeast. You can choose any one of them, but you must uniformly do that through your implementation and algorithm. Otherwise, you will keep drawing different lines for different situations. So don't keep choosing randomly when d is equal to 0. In one case you choose northeast, another case you choose east. No, your graphical software which you design must either choose consistently and uniformly northeast or east. In this algorithm which we have said that if d is equal to 0, choose east. So throughout we will follow that if d is negative or equal to 0, we choose east. If d is positive, we choose northeast. Okay, and we know in brief again we see in the case when we have chosen east, what we have to do is the following steps: increment the m by 1 along x direction, that the x coordinates of the midpoint is incremented by 1. Which gives us the new value of d nu, and that is obtained by incrementing the delta old by a value dy. We know that delta d east is d nu minus d old, which we have derived already, is equal to a is equal to dy, and so delta d east is dy, and in the case of northeast, the delta d northeast is given by dy minus dx. That is the one difference in the last two lines. Delta d under the case of east is dy, delta d or the difference of the decision variable under the case that when you have chosen northeast is dy minus dx. That is the main difference. The other difference is you have to increment m by 1 in both x and y directions in the case of northeast. In the case of east, you increment the x coordinates only by 1. So that's these are the two main differences in the choices. And where do you start with the value of d? What is the d at the initial position? Because you know the starting point, which is the starting point of the line given by x naught, y naught, and you keep incrementing by keep choosing east and northeast pixel, you have a starting point, correct? If you have a starting point in the some corner and this is the finishing point, let us say, so you have to keep traversing by choosing east or northeast pixels and incrementally and find the addressable pixels closest to the line. If this is the line, let us say, and then reach the final destination x1, y1, which is the ending point of the line, but you have to start. The starting point is known. What about the next? So you evaluate d at the starting point. You evaluate d at the starting point, which we say is our d start. So the d start, if you look into the expression, is given as f of x naught plus 1, y naught plus half. Why? Because you have to evaluate the d at the start for the first midpoint. First midpoint will be one more in the x coordinate and half along vertically along the y coordinates, and we substitute this expression and then try to resubstitute back the value of fx naught, y naught. You have this expression as ax naught plus a, by naught plus b by 2 plus c. I hope you remember the expression of f. Substitute these two. This is the expression you have, and you just borrow certain terms and find out that this can be easily written as fx naught, y naught plus a plus b by 2. Okay, you can be rewritten in this form, and you know f of x naught plus y naught. X naught, y naught, what it is? It is the starting point of the line, and the starting point of the line is lying on the line. So if that is so, then what you may have is you should have is the value of fx naught, y naught, which is the starting point and a point lying on the line. The value of f is equal to 0. So this term cancels out. The value of this term is equal to 0. You will be left only with a plus b by 2. And a and b are nothing but we know that they are dy and minus dx. So the value of the d at the start is given by dy minus dx by 2. That is the value of the d at the start, and then you keep looking at the sign of the d. We have seen the midpoint criteria. Based on the sign positive, negative or 0, you choose east and northeast, keep incrementing d using delta variables, keep on doing that iterations till you reach the end point. So that's the basic idea of the entire algorithm: a choice of midpoint criteria, incrementing the decision variable using integer arithmetic, and then keep on doing this incrementally at each iteration. But if you look back into the slide which I have just shown now, the expression of d start is given by dy minus dx by 2. dy and dx, which also comes in the expression of delta d, are integer coordinates, but dx by 2 is not guaranteed to be an integer. isn't it? You divide an integer by 2, you are not guaranteed to have an integer value. If this x by 2 is a floating point number, in fact, you are going to start d as a floating point number itself. So, we have a problem. We have a problem that d start itself should be an integer value. If it is not, it is a floating point value, then the entire algorithm turns to a floating point operation, and that will make the algorithm very slow. So, we have to start by making d start, or the starting value of the decision variable d, as an integer itself. Okay? You need to get rid of this fraction and see what we end up with all the variables. How to get rid of this fraction? Well, a simple suggestion is multiply the value of f by 2. If you multiply the value of f by 2, if f x y x naught y naught is equal to 0, then also 2 of f x naught y naught will be also equal to 0. So, the d will be 2d instead of d itself, and you will get the value of d as 2 dy minus dx. You multiply all of the variables, the starting and the increments, etc., everything by 2, and now you see that the decision variable at the start and the increments itself, which were again integers, multiplied by 2 will give you integer. So, you have integer arithmetic now starting from the initial value or starting value of d, which is called the d start or d init. You can also call it d init, the initial value of d. So, these are the expressions which we need to remember, which have to be used in the algorithm. So, let us look into the midpoint line algorithm now. We will look at the initial conditions first of the algorithm as given by the equations, and that is given by the x. We start with x equal to x naught, y equal to y naught, which is the initial condition. That means x naught, y naught is the starting point. So, initialize the current coordinates to be equal to x naught, y naught, and we also have the decision variables have to be defined. Before that, you define dy, which is the difference between y coordinates of the starting point and ending point of the line, y1 minus y naught. Dx is the x coordinates, x1 minus y naught. So, there is the first part of the initialization. Then the initializations continue, where the same set of equations are repeated. We have the d start equal to 2 dy minus dx, that is d start, the initial value of d. You do not have to write the d start here. The d starts with the value of 2 dy minus dx, and the two incremental values, which are also integer coordinates, delta d of E will be equal to 2 dy, del d of, under the case of northeast, will be 2 dy minus dx. So, that completes the process of initialization, and we can start with the loops. Of course, you start by first plotting the starting point itself, which is a plot point command, and we will see later on that this plot point commands not only plots the point at x y, but it also not only in the first octant, but it also plots the other cases. It also handles the other cases if the line is not in the first octant. We will see that. Okay. So, that is we are only worried about the first octant right now. Other 7 octants we will see how it is handled. So, the first point is drawn because at the initial case x is assigned to x naught, y is equal to y naught, and it has not been changed so far under initialization. And so, the first point which will be drawn by this command plot point, assume that is a low level graphics primitive command given to draw a point with a certain default color or shade with the value x comma y is will be having the value x naught, y naught. So, the first point is drawn, which is the starting point. Then this is the rest of the part of the midpoint line algorithm, and the entire part of the algorithm is given here. The rest of the part after the initialization, you can put actually everything in a while loop. You can also put it in a for loop, does not matter, and we keep on doing this iteration till x is reaching x1. We stop when x reaches x1, and so as long as x is less than the x coordinate is being incremented by unity from x naught towards x1, and as long as x is less than x1, we keep on repeating this while loop. And what do we do inside this while loop? As long as x is less than x1, okay, that we look into the sign of d. If it is negative or equal to 0, in comments I have put choose east. You choose east, and then what do you do basically is increment d by delta dE, which has been already initialized in this particular expression as 2 times dy. It is already initialized there. So, you increment d by that particular incremental variable, which is again integer. So, d is an integer, delta d also is an integer. That is how it is incremented. Else means you choose northeast, that means d is positive. You choose northeast in this condition because the line is above the midpoint M, basically the point M is below the line, and hence you have got a positive value of D. So, in that case basically you choose northeast, means you first increment the decision variable D here and also increment Y, because for both cases you need to increment X, which is also put under the expression here, that you basically increment X outside the if condition, and in one case only you increment Y when we are choosing the northeast, and you then plot the point again. So, this point, if you have this x y, if you have chosen east, will be only incremented in the x direction by 1. If you had to choose northeast based on the sign of D in the else condition, if you enter, what will happen is you have incremented y here, then you will again increment x, and you are basically have chosen the northeast as the current point of iteration of the pixel to be drawn or addressed, and you use the plot point with x y. So, you keep repeating this loop, keep on checking the sign of the decision variable. Based on that you choose east or northeast, increment the decision variable D, increment x in both cases, because you are always going from left to right in integer coordinates, increasing by unity. Only when you choose northeast you are incrementing by 1, as you can see here. You do not use this y is equal to y plus 1 under east, because you are only incrementing along the x direction. X coordinates will increase, y will not if you are choosing east. If you choose northeast, y is incremented here, and the x will be again incremented in both the cases. So, this loop keeps on incrementing till x reaches x1. You do not do this loop anymore when you are reaching x equal to x1, but as long as x is less than x1, you look into the condition put under the y loop, you have to keep on incrementing this decision variable and the x and y coordinates, x always, y depending upon whether you have chosen east only, not in the case of northeast you increment y, and the choice of the midpoint criteria is only look into the sign of D. So, the three conditions were look into the sign of D and then choose east or northeast and increment D. Okay. And then of course, the corresponding x and y coordinates obtained. So, this was the basic principle behind midpoint criteria or Bresenham's algorithm for drawing a line, and we have seen the algorithm starting from initialization of the D, x and y through the while loop. There is only incremental integer arithmetic of addition. There is no round function, there is no floating point. And this while loop will run very fast if you have dedicated hardware in the system and library functions for integer arithmetic, only incrementing by integers or incrementing xy coordinates, one of them or both by 1, and this will zip through and generate a few hundred points if necessary for a line. Even from the bottom left of your screen to the top right, let us say of your screen, you can actually draw a set of 100 points in a very fast time. It should be definitely a fraction of a second, not more than that, and that is possible because of the use of Bresenham's midpoint criteria of evaluating the line, evaluating the midpoint based on the sign of a decision variable, which is again integer, and incrementing using integer, incrementing xy coordinates by integer. So, it is integer arithmetic based, and that is the thing which we exploit. Why we could exploit that? We could exploit that because we were worried in the last lecture in the beginning of drawing lines that we were worried with floating point numbers and it will slow the system. We had to use round functions and all that. Those were all reasons why the algorithm was slowing down. We have thrown all of that now pure integer arithmetic, and we were able to use that because the entire space is discretized, digitized. It is a discrete space with integer xy coordinates. Since we are only move with integers, why worry with a floating point number? Although the value of the slope of the line m and could be a floating point number, we do not worry about that. Start with an integer and keep incrementing with integer values with the decision variable D. Look into the sign of D, find out your choice east or northeast, and then decide what's your next point. So, that's the basic idea, and we have seen the algorithm. You would please rework out the equations yourself to find out the decision variables D under east or northeast and also D start, and how did we multiply it by 2 to get rid of the floating point at the initialization phase itself. Midpoint line algorithm is assumed to be understood, but there are a couple of points here which one must mention. The first point which we must notice is, or take a fact, is that we assume that the points are only in the first octant. What about the rest of the 7 octants in the 2D space? That has to be handled. That is number one. And of course, there could be other points when the slope of the line is very low, that means close to 0 or very high. In fact, it is very close to 0. It's called a shallow line, when we also have some problems and some special cases, and also we'll look at the problems of aliasing of a line, which is not considered in Bresenham's. Aliasing of a line takes place due to the digitized environment. What the Bresenham lines algorithm solves or gives you a solution in very fast time is to find out the set of addressable pixels on the line which are the most closest to the line, which should be drawn or illuminated to give you the effect of a line drawn on the screen. So, we look into the first. We will take a small example of the Bresenham's algorithm and then move to see how the octants are addressed, rest of the octants. Let us say you take an example and apply Bresenham's algorithm to this and say the starting point is 5, 8 and the ending point is 9, 11 of the line. Okay. So, x naught y naught is 5, 8, x naught is 5, y naught is 8 and x1 is 9 and y1 is 11. If that is so, the initial line conditions is dy, which is y1 minus y naught 11 minus 8. So, dy is equal to 3. What is dx? It is x1 minus x naught 9 minus 5 is equal to 4. So, dx is equal to 4, dy is equal to 3. What is d start? Do you remember the expression of d start or the initial condition of d? It is 2 dy minus dx, correct? 2 multiplied by dy minus dx, and that expression will give you 2 multiplied by 3 minus 4, so it is 6 minus 4, d start is equal to 2. You see all integer values here. You need to have the initialized conditions in the case where you have the expressions of delta dE and delta d northeast. What is the expression for delta d east? It is 2 dy, if you remember that, correct. So, 2 dy is 3 multiplied by 2, which is 6. Okay. And what is the value of delta d northeast? Do you remember that? Let us look back and see the expressions. Delta d northeast is 2 multiplied by dy minus dx. You see the expression of delta d east, which is 2 dy. We have already seen that, that is a value 2 multiplied by 3, which is 6, and this is 2 into dy minus dx. So, let us go back to the example and we will see 2 into dy with 2 into 3 minus 4, 3 minus 4 is minus 1, so you get a minus 2 for delta d northeast. So, all the initialization is over. If the initialization is over, we start iterating now. So, the first point is the plot point x comma y, which is you start with 5 comma 8. So, that is drawn, that is the red pixel at x coordinate 5 and y coordinate 8 is clearly drawn on the left hand side of this square grid. Some small portion of the screen where x starts from 4 to 11, y from 6 to 13, small part of the screen is shown because you have to start from 5, 8 and let us hope we finish at 9, 11. If you do not finish at 9, 11, there is something wrong in the algorithm or there is, we have made some mistake in the calculation so far. We will see with a little bit of suspense whether we really wind up with the integer coordinates at 9, 11, this the finishing point. Okay. So, what is the initial value of d? D is equal to 2. Successive steps involves d equal to 2, which is a positive number. Positive number means the midpoint is below the line. So, midpoint is below the line, or you do not even worry about that, just look into the algorithm, you know if it is positive you have to choose northeast because northeast is closest to the line. So, if you have choose northeast, 5, 8 is the corresponding first starting point or current point of iteration at the start, the next point will be 6, 9. There are two choices, you can either choose 6, 8 or 6, 9, northeast is 6, 9. So, once you have chosen that 6, 9 and you have chosen northeast, you have to increment d by this value delta d northeast. So, what will be the value of d? It will be d start equal to 2 minus 2. So, d will have a value 0. d is equal to 0 will actually give you the next choice as the east pixel. We know if the value of d is 0 or less than 0, then of course, it means typically that the line is passing closer to east, the midpoint is above the line, and then so the next choice is 7, 9. So, that is the marked by the red. I hope you can see easily that the 7, 9. So, 2 more iterations are over after the initial point 5, 8. So, 7, 9 is east. So, you have to increment d by delta dE, which is the value 6 here. So, 0 plus 6 will give you 6. So, that is the new value of the decision variable d, which is given as 6, and it is positive, which by the decision midpoint criteria tells you that you have to choose the northeast point, which is with coordinates 8, 10. Okay, so, that is the point which is chosen now under the third iteration. First iteration gave us 6, 9, second 7, 9 and next 8, 10. We are almost reaching the end point now. So, now, but 8, 10 is northeast. So, delta d northeast is minus 2. Okay, you have to add this delta d northeast incremental variable to the decision variable d. So, 6 minus 2 will give you d is equal to 4. D is equal to 4 is what you get, and that again D is positive, and that gives you the value 9, 11. Okay, so that is the point which you draw as the finishing point of the line, and here you find out that you have reached a value x equal to x1, x is 9, which is equal to the ending point x coordinates 9. You don't do any more iterations. So our suspense is over. We have started with 5, 8, and we have reached 9, 11 without worrying about the ending point. Okay, so that means the algorithm is correct. We have not made any mistakes in the calculation. This is just a sequence of steps taken by an example where which you should work out yourself to see that you start with the decision variable. Take any 2 points. Take any 2 points. 5, 8, 9, 11 is taken in this case, but you can take any 2 integer coordinates. Only assume you are in the first octant. Slope is less than 1. That is what you should assume, and then just apply these little bit of steps for the decision variable d based on the sign and incremental algorithm of delta d east or northeast, and keep incrementing and select your east or northeast successively, and see that if you are reaching the ending point. Okay, so I'll repeat this set of successive steps once again. This was the starting point, and then first variable d is equal to 2, so choose 6, 9, then d is equal to 0, you choose 7, 9, then you have d is equal to 6, it gives you 8, 10, and then again d is equal to 4, you actually choose the last point 9, 11. So that's the example which you have taken. I do encourage that you should take some more examples to get used to applying this algorithm. Okay, and this was the line. This blue line, dashed line, shows the line on the screen, which is the ideal line, the what I will say as a in the analog world, non-discretized space was the continuous line shown in by the dashed blue line, and you can see that the points are spread around, and the 3 points which you have chosen between the starting and the ending point of the line are the closest possible addressable pixels. Addressable pixels are the intersection points of the grids in this case, and these 3 points are the ones which you are close. You will not be able to find any other point which is closer than these 3 set of points to draw a line. So that is the enough proof that the Bressenham's midpoint criteria works really very well. Okay. Now let us think about the other octants. Okay. In the time left in this lecture, we will worry about the other 8 different octants, 7 other octants, because we have only worked on the first octant, the slope is less than 1, and we will worry about the 7 other octants. So we look back into this figure. If you remember that we had shown this figure earlier in the last class, where we have considered lines only in the first octant marked in the blue color as 1, and what about the rest? That means if the lines lie in any of the other 7 octants starting from 2 to 8, that means the slope could be more than 1, it could be negative, and so on. The starting point could be on the right hand side with respect to the left hand side, that means x naught is more than x1. What do you do? Well, you have to make some initialization as an overhead to change the scenario to quadrant number 1 and then apply the Bressenham's, because if all the other 7 situations can be converted using some sort of a symmetrical nature of this distribution of octants, then and every line can be pose equivalent to or mapped onto quadrant number 1, and you get the integer coordinates in quadrant number 1 and then map it back and put it in the other quadrant as the case may be, depending upon whether you are at 2, 3, 4, 5, 6 or 7 or 8 quadrant, then you have solved the problem. What do you do? Well, how do you generalize this to other octants? These are the cases. So this must be as an overhead which you have to write a small code before you actually apply the Bressenham's algorithm, and these what we will do basically is take your line into the first octant, get the points, and then apply it back. So when you are in the first octant, do not make any change, because you already know the Bressenham algorithm here. In all the other octants, you see here, there are basically 2 important statements. One is switch roles of x and y is the statement which you find for octant number 2, 3 and 7. And this is one statement. The other statement which you find is draw from P1 to P0. Okay. I will try to discuss a few of these cases in the available time, and you can I leave it as an exercise for you to check for the other octants as well, and see how this helps you. Let us move into this figure. You remember we have solved the problem in octant number 1 where this line is drawn. What about octant number 2? Octant number 2 tells you that the line is having a slope more than 1. If the line is having slope more than 1, what you can do is the change which you need to put is switch roles of x and y. That means the x coordinates should be considered as y coordinates now, and vice versa. If we make this change, what you are basically doing is mapping the quadrant 2 onto the quadrant number 1, okay, or basically reducing the slope from more than 1 to less than 1. Find the coordinates in the first octant, but since x is now y and vice versa, you will be actually putting the plotting the coordinates in the second quadrant origin itself. So the second quadrant is very easy to visualize. When you switch roles x and y, you are basically done the job. What about quadrant number 3? This is a unique case where the slope is not only more than 1, but it is negative. It is negative, and then you say that you switch roles from of x and y. Not only do that, but use number 4, which says draw from P1 to P0. Now, quadrant number 3 forces you to a scenario where you are not drawing from left to right anymore. We have talked about an initial point to your left and the final point to your right. Now it has been swapped. Swap means this is the initial point and this is the final point, and you are drawing in the third quadrant, mind you. So the slope is also negative, and you are drawing from the starting point to the finishing point, and this is the starting point which is to your right, and the finishing point is to your left. So you have to reverse the role. So you have to swap the roles of not only x and y to bring the slope less than 1, but you have to actually also draw from the reverse. Draw from, instead of having P0 to P1, you draw from P1 to P0. Apply the reverse role. So you are basically drawing left to right, and then of course changing the. So that is what is done for octant number 3, where you use not only switch roles of x and y, use number 4 which says draw from P1 to P0, and then use number 8 where it says keep decrementing y instead of incrementing y. We have been incrementing x and incrementing y. In this case, you increment x and decrement y. Okay. So these are, I leave the rest of the octants for you to check up. We have only discussed quadrant number 2 and 3. I leave the octants number 4, 5 to 8 with you, but we have to see the section of the code which is involved in those two simple constructs or cases where you change the roles of x and y and draw from P1 to P0. This draw from P1 to P0 in terms of coding means swap P0 to P1 and decrement y or decrement delta dy as well. Okay. So this is what is given here. Draw from P1 to P0. The statement involves the following two codes: swap P0 P1, that means make P0 equal to P1 and P1 equal to P0, and decrement y and make dy equals minus dy. So that will automatically happen. So basically going down instead of going up, and switch roles of x and y is swap x1 y1, swap x0 y0. It typically means that your x becomes y and y becomes x. You also swap the values of dx and dy, which was used to initialize the variables, and then you plot a point as yx instead of x comma y. So once you do that, automatically the octants are taken care of. So these are the two cases for drawing a line in all the other quadrants. I will leave with the minimum amount of time left about the problem of aliasing. But before that, I must tell you that you please discuss among yourselves and try to solve the problem of all the other octants. I have discussed octant number 1, 2 and 3 only, and I have given the statements for octants 4, 5, 6, 7 and 8 in this slide just a few minutes back, and you should try to see with this role of reversing P0, P1, reversing the role of x and y, whether the statements are correct and you are able to draw the line correctly. Well, in addition to the problem of drawing a line in all the other octants, the main issue was the effect of Jaggies or staircasing. I will pose the problem. We have discussed this problem also in the last class, which is bound to happen in the digitized environment. And this figure, as you see in the slide here, now I have shown pixels not as the intersection of grid points, but within the squares. So assuming you have a starting point at 5, 8 as like the previous problem, and the finishing point is 9, 11, and we have calculated ourselves the following few points, and if these points are enlightened, you can see that there is a big effect of staircasing. So how do you handle this effect of staircasing to make the line appear more smoother? That is the effect which we have to see. We will work on that in the next class when we meet. So the issues are staircasing. You can have a problem of drawing fat lines, which are either a line with 1 pixel wide, or even it could be 2 or 3 pixels or n pixels wide. You have problems of uniformity of drawing this. And the other problem which I want to leave with you is the endpoint ordering is also very, very important. Endpoint ordering means if you want to draw one line one after another, and each of these lines have different color, different width and different shading. What about the endpoint? In this case, as you say that you drawn a red line, then a blue line and then a yellow line, what happens to the intersection points of these two lines? The starting and the initial and the finishing points will have the red color and the yellow color, all right, but do you want this intersection point of these lines to have the color of the middle line or the red line or the yellow line? These are all important issues which one has to think about while designing his algorithm in terms of implementation. Whichever gives the best view in terms of the entire figure, we have to solve. Of course, we will discuss in the next class the effect of Jaggi staircasing or aliasing for drawing lines and mainly, but there are other issues involved in fact lines and also in endpoint ordering, which one must take care when drawing lines. We will start with this slide when we meet in the next hour. Till then, goodbye. Thank you.